Okay, this second video is a demonstration of the use of BATHTUB based on a study done by Limnotech doing a TMDL for total phosphorus for Medicine Lake. Medicine Lake is located in the western suburbs of the Twin Cities. Here you see the boundaries of the watershed, and you can see Medicine Lake Interstate Highway 494 and 394 are visible on the map, so you get a perspective on where this is located. The major tributaries for the lake are shown here. There are 10 sub-tributaries that were mapped out for the lake, and these were monitored for runoff and for total phosphorus entering the lake. And as I'll show, those the runoff and the total phosphorus loads were also modeled using the P8 model. As required for BATHTUB, one of the input data include the bathymetry of the lake, and you can see here the bathymetry information for the lake, a couple of different bays for the lake. The model that will be shown is for the main body of the lake. Monitoring data available for the lake is shown at the solid red circle location, which was sampling that was done on a periodic basis, including total phosphorus and Secchi disk depth, as well as chlorophyll A. And then there was also a automatic data recording system called RUS located at where the solid yellow circle is. This would be an instrumentation system set up on a float that recorded data in the water column all the way down to the bottom of the lake on a continuous basis. Things such as total oxygen, temperature would have been available from that location. The land use for the lake is necessary for the P8 modeling and also for making recommendations on how to change practices in the watershed. And you can see here that much of the watershed is developed. There's actually very little room for further development in the watershed. Some areas here have very high impervious surfaces, high percent of impervious surface. So a very large option or very large potential for runoff generation as well as phosphorus loading. And we'll talk a bit about later, or I'll refer to the P8 modeling. I'll also refer to a thing called reserve capacity, which has to do with the possible amount of potential further growth in the watershed, and that value was set to 0 because the lake is the watershed is so developed here. One source of total phosphorus for the lake is the internal load from the decay of curly pondweed, and so it was necessary to have the distribution of the curly pondweed for the lake. And this shows the a map of the distribution of curly pondweed, representing the highly dense regions, the moderate and then low regions of concentration of curly pondweed. I'll talk more detail about how the total phosphorus from curly pondweed was estimated. Okay, here you can see the sampling from the that location where the solid red circle was, that sampling location. Total phosphorus would be measured at that location on a monthly basis, and then this is the annual average values that are shown. And we can see that the annual average values are well above 40 microgram per liter, which is the water quality standard for this lake. Data goes from 1995 through 2007. Also, Secchi disk depth and chlorophyll A were measured at that same location. And you can see Secchi disk depths are about a minimum of a little over a meter and go down to about 2¼ meters maximum. And then the chlorophyll A values are hovering around, well, they range between about 10 microgram per liter up to about 30. The Secchi disk depth, the chlorophyll A, and total phosphorus are all used for characterizing the eutrophication status of the lake. You'll see this when you apply the bathtub model. I'll be providing you with information on how to come up with that eutrophication status based on these three variables. All right, P8 modeling. P8 is a model that was developed by the U.S. Environmental Protection Agency. The model for runoff and generation, as well as for constituent transport. In this case, the constituent is total phosphorus. You can see we've got 11 tributaries. I think I mentioned before there were 10. There's 11 subtributaries. The study was done for the period from 2004 through 2007. The P8 modeling was used to predict flow and total phosphorus in these subtributaries, all contributing to Medicine Lake. The purpose of the P8 modeling is to develop a model that could be validated, or I should say calibrated and then validated for the watershed. And once we know that it does accurate predictions or makes accurate predictions of both flow and total phosphorus, that model could then be used to determine what effect there would be if we were to change the land use practices in the watershed. So the model was was calibrated for the watershed, comparing flow predictions, which are shown here for 2006 conditions. For the various subtributaries, and you can see that the model does a fairly good job of for the calibration for predicting the runoff, and then also for total phosphorus load, again for 2006 conditions. All right, so here shows the mean water quality conditions for Medicine Lake for those 4 years. 2004 through 2007. Highest total phosphorus was in 2004. Second highest was in 2007, and lowest was in 2006. 2006 conditions were used for calibration of the BATHTUB model, and I'll explain the reason for that selection of 2006 here as we go through this. So the BATHTUB model was calibrated for 2006 data, as already mentioned, and then it was validated for the period, or for the years 2004, 2005, and 2007. 2006 was used as a calibration year because it was assessed that that was the year in which there was minimal amount of internal loading of total phosphorus. Basically, the only loading to the lake was from the watershed and those tributaries, and then also from atmospheric loading. The reason the model would be calibrated for just 2006 when there was little internal loading is because the internal loading component is very difficult to estimate. So by eliminating that from the 2006 model, it's possible to focus just on the watershed loading as well as the atmospheric loading. So the model was used without any internal loading to predict the observed total phosphorus, chlorophyll A, and Secchi disk depth. And you can see the observed values for total phosphorus, chlorophyll A, and Secchi disk depth, and then they predicted BATHTUB values, which are very close. This is based on changing the parameters in the model and coming up, finding the best set of parameters that give the best prediction of the observed data. Several models that were used within BATHTUB are shown in the fourth column. For instance, Canfield-Bachmann Lake component, the Jones and Bachmann component, and then the chlorophyll A and turbidity component. These were components that could be selected when you're using the BATHTUB model, and you'll see that when you get a chance to apply the model. Okay, so as mentioned at the bottom, internal loading was minimal in 2006, or at least it was assessed, because one thing is that the curly pondweed growth was subdued in that particular year, and also based on the data from the Russ monitoring station, which measures the oxygen profile in the lake and also temperature profile, it was determined that that was a year in which there was minimal lake mixing. The lake mixing is important because what the mixing of the lake does is to bring all the high phosphorus that would be at the near the lake sediments in the bottom of the lake up to the surface, and that would then, by having a well-mixed lake, you would be actually increasing the phosphorus concentration in the lake as a result of that internal load from the bottom of the lake. All right, so the model calibration is shown here. The yellow bars are the watershed loading in pounds per year for total phosphorus. The observed water quality in the lake in microgram per liter is shown by the yellow diamonds, or the green diamonds, and we can see that the predicted water quality in the lake, which is the yellow squares, is essentially perfect for the 2006 conditions, with the watershed load of 4,517, which is a measured watershed load, and this would be with no internal loading component. 2005 is predicted quite well as well. 2004 and 2007 were not well predicted here, and that's because there is obviously some internal loading component that's missing from those 2 years. So the model was, by trial and error, the internal loading for 2004 and 2007 was increased until you got a good match for the observed water quality in the lake, and that's shown in this slide. For 2004, it required an internal loading component of 4,770 pounds per year, and for 2007, it required 3,693 pounds per year. And for those conditions, with the watershed loading that's observed for each of those years, the match was very good for the total phosphorus. So the whole thing about internal loading comes from the sediment on the lake bottom. When the lake bottom becomes anoxic, that is, when the water in the lake, near the lake bottom becomes anoxic, phosphorus is released from the sediment. And a model called the Nuremberg model from 1988 and 1995, that model was used to estimate that internal loading from sediment. And then curly pondweed, because a survey was done to determine the mass of curly pondweed for the 2004 year, the samples of curly pondweed were taken. The total phosphorus in that biomass was determined, and then by knowing or by estimating the mass of curly pondweed around the lake and knowing the content of total phosphorus in that curly pondweed mass, it was possible to estimate how much phosphorus would be released into the water column in June and July period, when curly pondweed typically senesces and dies off and decays. So at the very top, it says BATHTUB modeling yielded an estimate of 4,232 pounds per year. That's just the average of the 2004 and the 2007 calibrated values that gave good water quality predictions by the BATHTUB model. So the two numbers, 4,770 plus 3,693 averaged together gives you the 4,232. So we'll compare that 4,232 to the independent estimate of the amount of internal loading from sediment and curly pondweed, which follows. Before I get to that, just first talk about the process in which the mixing can affect the water quality in the column of the lake. This is from the Russ unit. The green color shows the high oxygen concentration. The black shows the low oxygen concentration. This is for July and August in the lake at that location, and you can see that there's large periods of time which conditions at the bottom of the lake are essentially anoxic. Under those anoxic conditions, the lake is the sediment is releasing total phosphorus into the water column, or just near the lake bottom. What's shown here is that when you see those spikes of the green going down to large depth, that's when there's mixing of the shallower water with the deeper water. And during those periods of time, there would be the lake would be well mixed. All that phosphorus that would be generated near the bottom of the lake would actually be mixed with the surface portion of the lake. And that would increase the phosphorus concentration in the water column. And that would, of course, be measured as being a high phosphorus concentration. This shows the slide for 2006 conditions, shows the oxygen concentration in the water column, and those concentrations are greatly reduced in June, July, and August, the period when internal loading is the worst within the lake. And here we see the total phosphorus concentration near the bottom of the lake for all 4 years. You can see the maximum total phosphorus concentration near the bottom of the lake in 2007 was almost 1,600 microgram per liter. Compare that to the 40 microgram per liter water quality standard. And in 2004, the maximum value is about 600 microgram per liter. So you can imagine that if this water near the bottom of the lake, which has very high total phosphorus concentration, is mixed with the surface portions of the lake, that would greatly increase the phosphorus that would be measured during the sampling times. All right, so this Nuremberg model is shown here. A very simple model. It gives you or estimates the amount of total phosphorus that's being generated at the interface between the lake and the bottom sediments. It's expressed in milligrams of phosphorus per day being generated, and it has a number of factors in it. The parameters that are given here, for instance, for the anoxic factor, were generated using a model called Aquatox, and which is an EPA model. And this was for the 2006 Medicine Lake observation data that was recorded. And so that model estimated that the amount of phosphorus that's released was between 4 and 9 milligrams per square meter per day. This is an input that we would actually put into the BATHTUB model, and you'll see that when you actually apply it. In any case, 2006 conditions were used for this Nuremberg model. Later I'll mention that maybe those conditions aren't the best conditions to use, but that's what it came up with. Okay. The final figure then was that the amount of internal load from the lake bottom, the bottom sediments, was 1,834 pounds of total phosphorus. As evidence of the effect of curly pondweed die-off and decay, What's shown here is the total phosphorus in the lake for 2003. You can see that the concentration takes a big spike or jumps up in July, the time when the curly pondweed is at its peak die-off. So this would be evidence that perhaps curly pondweed die-off is another source of high total phosphorus in the lake. Estimate of the loading from curly pondweed samples were taken in 2004. The area of curly pondweed distribution, as well as the total phosphorus in the biomass, was all measured, and from those estimates from the sampling that was done, the total phosphorus loading from decay of the curly pondweed was estimated to be 1,050 pounds. So if you add those two numbers together from the sediment and the curly pondweed, you come up with 2884. The BATHTUB model estimated that the amount would have to be about 4,232. There are a number of explanations for the underprediction from the that was done independently, and those are listed here. One would be the anoxic factor, which was derived from the Aquatox model. It was 49 days. That perhaps the reason that it was underpredicted is because they were using 2006 data from the Rush unit, and the observed condition was 102 days for the anoxic factor. So it's just that the 2006 data were not dynamic enough. There wasn't enough mixing going on in the lake, creating conditions that would make it so that the model would underpredict that anoxic factor. Another might be that the phosphorus coming from the sediments may not only come from the mineral material on the bottom, but also decay of organic matter near the sediment interface. It's already mentioned about the fact that perhaps the using 2006 information to model the dynamics of the hypolimnion may not be sufficient. And then also it may be that the curly pondweed total phosphorus mass may be underestimated. Okay, so now the BATHTUB model was used to look at the sensitivity of the phosphorus in the water column without the internal loading component. So this graph is for the response of the lake water quality total phosphorus concentration to watershed load without consideration for the internal load. And it's shown here that when the lake is at 40 microgram per liter, that would be for a total phosphorus load of 3,500 pounds per year. So if we wanted to match the water quality standard of 40 microgram per liter, we would not allow more than 3,500 pounds of phosphorus load from the watershed per year. There's an additional 253 pounds per year that's coming from, estimated to be coming from atmospheric deposition. That number comes from a bioengineering study for the Twin Cities region. The sensitivity of the model was, it's a feature that the BATHTUB model has in it, that it will take various values of the watershed load. These are just hypothetical loadings. And so you can see that for loading of about 1,000 pounds coming from the watershed, the phosphorus concentration in the lake would be about 19 microgram per liter. For 9,000 pounds, the loading would be about 68, or the concentration would be about 68. And the intersection point, as I've already mentioned, is 40 microgram per liter would be watershed load of 3,500 pounds. Now, of course, for the watershed, we have over 4,500 pounds being loaded to the watershed, and that's how we get the 45 microgram per liter in 2006 conditions. Generally, we for the TMDL equation, we have an explicit or an implicit margin of safety. And for this case, the margin of safety was set based on using a more restrictive target. So instead of 40 microgram per liter, which would be the water quality standard, it was decided that we'd use 38 microgram per liter. So from our sensitivity curve, the 38 microgram per liter is generated using a watershed load of 3,230 pounds per year. Okay, so the watershed load is 3,230. The BATHTUB model also accounts for the 253 pounds per year coming from atmospheric. And as I already mentioned, the internal load is set to 0 here, so it's assumed that there is no internal load. Here's the TMDL equation. It's just the sum of the waste load allocations, the load allocation, which would be non-point source pollution, and then the margin of safety and the reserve capacity. For this study, the TMDL was set to 3,753 pounds per year. The watershed load application was set to 3,230 pounds per year. The load allocation was 253 pounds per year. The MOS was 270 pounds per year. And the reserve capacity, as I mentioned earlier, because the watershed has very little room for any further development, was set to 0. Okay, so the MOS was 270 pounds per year. That's the value that would give you, if you would incorporated that into the analysis, would give you the 38, the more restrictive water quality standard of 38 microgram per liter that I had already mentioned. Now, the watershed load the waste load allocation is 3230. And the reason why is there are no wastewater treatment plants here. Basically, it's just municipal stormwater that's being accounted for here. And so there is no really non-point sources except for the atmospheric load coming into the atmospheric loading, which was estimated to be 253 pounds per year for the watershed. So the MS4s are the part that make up the waste load allocation. It'd be all the runoff from the streets and parking lots and so forth that gives you the 3,000, or is allocated to the 3,230 pounds per year for the TMDL equation. Okay, so the explanation is given here for each of those. Okay, so the reductions in phosphorus loadings to meet that TMDL, the watershed load is 4,517. That number was given earlier. To meet the water quality standard, the watershed load can only be a maximum of 3,230. So we need a reduction from the current conditions to meet the water quality standard of 1,287 pounds per year. That's a 28% reduction. For the atmospheric, we can't really do anything about that. It's just a given. Again, that was estimated by Bar Engineering for this region. So there's no reduction for the atmospheric. For internal loading, we gave a very large number, or derived a very large number of 4,232. Part of it's from sediment, and part of it's from the curly pondweed. It's assumed that somehow this can be taken care of to reduce it to 0, so that there's 100% reduction. What that requires is curly pondweed control, and also somehow making it so that the reducing the amount of internal loading from the sediment, perhaps by providing some mechanism for increasing the oxygen concentration at the bottom of the lake, or else at least reducing the amount of mixing that occurs in the lake. Margin of safety was set to 270. So under current conditions, we have a total of 9,000 pounds per year occurring. The TMDL says that equation to meet the water quality standard with the MOS and so forth is 3,753 would be allowed. The reduction is 5,519, or a 61% reduction is what's required. Okay, so as I already mentioned here, internal loading is assumed is proposed to reduce to zero. How you go about doing that is a matter of engineering design. Okay, so here's again the response curve. This is for 2006 conditions. The current conditions are a watershed load of 4,517 pounds. Again, this does not include the internal loading. The internal loading is assumed to be zero. To meet the 40 microgram per liter, we would allow a watershed load of 3,500 pounds. On top of that would be the 253 pounds of atmospheric load. With the 3,500 pounds and the 253 pound atmospheric load, it would give 40 micrograms per liter. And then for the more restrictive condition, if we assume a 270 pound per year MOS, the watershed load would be 3,270 pounds. That's just 3,500 minus 2,070. So the watershed load would be 3,230 pounds. Add on to that the 253 pounds of atmospheric load. That the BATHTUB model would say that the water quality in the column would be 38 microgram per liter. All right, so here's the MS4 boundaries for the watershed individually. Number of different cities and municipalities here. MS4s are areas that have more than 10,000 people. Each of these MS4s then are somehow responsible for the total load that's going into the lake. And this gives detail on those MS4s. Other sources would be MnDOT because of the Highway 494 and 394. So the watershed is mostly made up of MS4s. 96.3% of the watershed is made up of MS4s. There's Hennepin County has some responsibility, about 171 acres. MnDOT has 260 acres represented. So if we take the total load that's going to be allowed, it was really 3,230 pounds. 3,105 would be the responsibility of the municipalities that are shown there, the MS4s that are shown. 48 pounds per year would be the responsibility of Hennepin County, and then MnDOT would be responsible for 71. The 3,230 pounds is when we reduce it by 6, because there are 2 industrial discharges that are estimated to be 6 pounds per year, would come up with a total of 3,224 pounds allocated to the MS4s. So just explaining why it was not 3,230. It's reduced by 6 because of those industrial discharges. Now, one way in which the TMDL could be handled would be that those cities would then break up or would be responsible for their portion of the 3,105 pounds based on their watershed area. Their fraction of watershed area. They could also come up with some other scheme to divvy up that amount of total load that's required to be handled. So the idea would be that each of the cities would be responsible to reduce their load so that they're not contributing more than the amounts that are given here. And with that, ends that video.